Welcome to Statistics Review Part 6. In this video, I'm going to talk about simple random samples. I'm going to talk about stratified random sampling and how that's different. Different kinds of data that we might have in our sample include time series and cross-sectional, so I'll mention those. And then I'm going to talk a little bit about the central limit theorem. So to start off here, a random sample from an infinite population is a sample selected such that the following conditions are satisfied. Each element selected comes from the population of interest, and each element is selected independently. Then, for a simple random sample, each element has the same probability of being drawn. So no given element is any more likely than any other to be included in the sample. A different kind of sampling, though, is stratified random sampling. So in this case, the population is first divided into groups of elements, and these are called strata, and each element in the population belongs to one, and only one, stratum. So examples of strata that we might have, we could have a group of non-high school graduates, high school graduates, and college graduates. So each person might be in one of those three groups. We could also have firms divided into multinational and non-multinationals. A simple random sample is then taken from each stratum. So for example, in the previous case, if we had multinational and non-multinational firms, we would take a random sample of multinational firms and a random sample of non-multinational firms, and that is how we would go about that. So an advantage is that if the strata are homogeneous, this method is just as precise as simple random sampling, but with a smaller total sample size. And again, some examples here, we could use strata. They might be based on department within an organization, location, so geography, age, could be industry type, even in the example before, multinational, non-multinational, or other things similarly. We also have time series and cross-section data. So the sample, the data that we are collecting, could consist of observations from a time series or a cross-section, or it could be a combination of those. So with a time series, the observations are taken at different points in time, and an example might be the price of coffee at one store, and it gets recorded in January, so pick a date in January, in February, in March, April, May, and so on. Whereas a cross-section, the observations are taken at one point in time from different elements. In this case, if we're thinking about coffee prices and stores, then we might look at the price of coffee on January 1st, but different elements would be maybe different stores, and that would be an example of a cross-section. However the data are obtained, whether it's time series or cross-section or some combination, once we have them, we might perform a type of statistical inference. We might get what is called a point estimate. So we're doing point estimation. In point estimation, we would use the data to compute a value of what we call a sample statistic. That's some function of the data that serves as an estimate for our population parameter. So here, we're to distinguish between population parameters and our point estimators. So in this case here, if we were thinking about the mean, x bar is a point estimator for the population parameter mu. S is a point estimator for a population parameter for the standard deviation, sigma. And we could have a proportion, in which case p bar is a point estimator for the population parameter, proportion, which would be p, using this notation here. So to estimate the value of a population parameter, so that would be something like mu, we can compute the corresponding characteristic of the sample, so from the data that we selected or that we collected. So this is going to be referred to as a sample statistic. So for example, x bar is a sample statistic. We might use it to estimate, again, mu. Mu is the population parameter for the mean, the population mean. So with that, we have x bar as a sample statistic. We're curious about the sampling distribution of x bar. That is the probability distribution of all possible values for the sample mean x bar. So to clarify here, we could grab one sample that leads to x bar being 20, and we could grab another sample that leads to x bar being 21, and we could grab a different sample which leads to x bar being even some other value. So we have a lot of different possible values that could result for x bar depending on the sample that we collect. So the expected value of x bar is mu, right? That is the population mean. Now, if this is the case, that the expected value of x bar is mu, then, and x bar again is the point estimator, then we say that the point estimator is unbiased. So it is possible to have an estimator, a point estimator, for which the expected value is not the same as the population parameter. But for x bar, this is the case, and so x bar is unbiased, has this quality here. Right, so in essence, on average, we expect that x bar will be correct, that it will tell us what mu is. However, not all values for x bar would be the same. Again, it depends on the sample that we get. Some notation that we could use, this sigma with the little x bar underneath, and that is the standard deviation of x bar, because again, we could get different values for x bar if we were to collect different samples. Now, what is the formula for this standard deviation for the sampling distribution? It is the population standard deviation here, sigma, divided by the square root of n. This formula here is referred to as the standard error of the mean, or sometimes people simply say standard error. But that gives us what the standard deviation is for the distribution of sample means. Now when the population has a normal distribution, so the underlying random variable is normally distributed, the sampling distribution of x bar is also normally distributed, regardless of the sample size. Now in most applications, the sampling distribution of x bar can be approximated by a normal distribution whenever the sample is of size 30 or more. And the sampling distribution of x bar can be used then to provide probability information about how close the sample mean, x bar, is to the population mean. Because if we are approximating it with a normal distribution, we have probability information about the normal distribution. This is summarized here in what is known as the central limit theorem. So when the population from which we are selecting a random sample does not have a normal distribution, so it could be uniform, it could be anything, the central limit theorem is helpful in identifying the shape of the sampling distribution of x, right? And that is, or x bar rather, and that is that that is distributed approximately normal, right? So what this says is that in selecting random samples of size n from a population, the sampling distribution of the sample mean, x bar, can be approximated by a normal distribution as the sample size becomes large. And as I said a minute ago, in practice, what we find is that typically the number for being large is that if n is 30 or larger, this condition will typically be satisfied. And in this case, then, x bar will be normally distributed with mean mu and standard deviation equal to sigma over the square root of n.